Hi everyone, I'm Matt Hansen. I'm from Intel Corporation, and I'm here to talk to you about Navigation 2, which is the next generation navigation on ROS2. First, a quick note on where I work. So I work at Intel in open source robotics, which is part of the Open Source Technology Center at Intel. You may not know, but Intel is one of the biggest contributors to open source software in the world. We're the #1 contributor to the Linux kernel, and we work on Chrome OS, Android, OpenStack, OpenCV, many other technologies. Pretty much most of the major open source systems out there in the world we've contributed to in some way. And we are a technology company. As you know, we are, virtualization, AI, machine vision, real time. These are all technologies that we have that we're enabling in robotics using ROS2, and navigation is one of those projects that is making that possible. So one quick kind of background on navigation is that if you're not aware, on ROS1, navigation is one of the most used packages there is. It allows you to drive a robot autonomously from point A to point B. And back in 2018, we started looking at it as who was going to port this to ROS2. We knew it was kind of a big roadblock for ROS2 adoption within the community, and there wasn't a lot of momentum yet in that area. So we kind of stepped in and said, well, we would help or lead the effort in doing a port of navigation from ROS to ROS2. So that was kind of how the Navigation 2 project was started. To begin, we wanted to take a kind of fresh look at things, and so I posted to discourse.ros.org and asked for input from the community and said, what would you guys like to see changed or improved in ROS2 navigation versus ROS1? And got quite a few responses that were kind of all over the board, but there was kind of some recurring themes that emerged from that. Things like customizable logic, modularity, extensibility, and then in addition, there was things that we as software engineers wanted to be able to do to make the software more reliable, higher quality, and more maintainable. So we kind of defined a set of requirements around all these goals and set out to attempt to meet those requirements, and that's the Navigation 2 project. So some of the things that we did to add extensibility, flexibility, modularization, and reliability are we removed move base and we replaced it with behavior trees, which I'll talk a lot about in a few slides. We changed the way that planners are integrated with what was move base with the behavior tree now by basically putting in ROS2 actions as interfaces to those, and then we've done the same thing with recovery behaviors now. And then for reliability and stability, we moved all the nodes to ROS2 lifecycle nodes, which I'll also talk about. So if you're familiar with the ROS1 navigation stack, you probably have seen this picture before. So a lot of the components that were there in the Nav1 stack are ported to ROS2, but not all of them. So I'll go through them one by one here. The simplest place to begin is with AMCL and map server, because they were pretty straightforward ports, and there wasn't a lot of re-architecting that needed to be done there. We did do some code cleanup, and we did some refactoring to try to make the code more extensible as far as being able to add other map types in the future, things like besides just occupancy grids, like grid maps and things like that. But for the most part, those are pretty straightforward ports. For move base, as I mentioned before, that was really replaced by behavior trees. So we have a new node called BT Navigator. Recovery behaviors, as I also mentioned, these are now callable actions from the behavior tree, which allows you to configure what recovery behaviors you want in what locations and what order you want to call them in. The global planner, we ported the NavFN planner, if you're familiar with that, from the ROSCon navigation stack. The local planner, we took the evolved DWA planner, which is in robot localization from David Liu, that's called DWB, and we ported that into the Nav2 stack. And for the global cost map and the local cost map, we ported those, and they're basically plugins similarly to how they were in ROS1. They're within the global planner and the local planner, respectively. One other thing to add, and I mentioned, was that since this is all actions-based now, so we added new planner server and controller server and also recovery behavior server that are all callable through action interfaces. So this is kind of a high-level picture of what the architecture looks like now. So at the top you have navigate to pose, which is an action that you send to the stack. BT Navigator is basically a action server for that navigate to pose that you can give it a behavior tree, which is in the form of an XML file, and I'll show you that. And then based on what's in that XML file, that kind of controls the flow of how things work. But the default flow is there's the planner server and the controller server. They're servers for the compute path to pose and the follow path actions, respectively. And then within those, as you can see, there's the plugins for the NavFN planner, the global cost map, and then the DWB planner and the local cost map. Most of these other components are, you know, basically, as I said, kind of straight ports from ROS1. So I've mentioned behavior trees a couple times. Can I get a show of hands? Is there anybody in here who has used behavior trees before? Okay, good. So there's, yeah, all right. There's quite a few of you that have. That's good. Less than half, but it's a start. So behavior trees are similar to like a state machine, but it's actually kind of almost like a binary tree. So you can go down one path and then you can go down another path. This is an example taken straight from their website, but basically, so there's like a sequence node which will execute the right branch of the tree, and then it will execute the left branch of the tree. So we'll start by going to the retry until successful, which is what it sounds like. It will just keep retrying whatever its child is until its child returns success. And then you have a fallback node, which basically it's like an if then else. So if the first thing is true, then it returns, otherwise it does the second thing. So it gets down here and it says, is this clear? If not, then read the documentation. Retry until successful. So keep reading the documentation until it's clear. At that point, then you can build awesome robots. So that's the behavior tree in a nutshell. So this is a more complex example, basically, of what we're doing in navigation 2 with the behavior tree. And this is a little bit abstracted, so it's, you know, it's not a absolute representation with all the details, but to give you the concept. But basically, as you can see on the left side, that's the navigate flow. And so there's the, on the bottom left, you'll see there's a question, has the goal been reached? If not, then compute the path to the goal, and that will actually, you know, invoke the action compute path. And then it will go to the follow path side of that tree, and it will pass the path to the follow path, which then obviously tries to follow that. And what we have here is we're running the compute path at 1 hertz, so it's constantly, every 1 second, it computes a new path and passes it to the follow path so that it's constantly looking for a better path to follow. And then if that fails, it goes to the recovery flow on the right side here, which has actions like clearing the global cost maps, clearing the local cost map, and spinning. And that's extensible, and we have other actions as well, but this is kind of the default right now. And then on the left side shows you the XML representation of all this. I'm not going to go through that line by line, but just to give you an idea of how you write a behavior tree like this, you know, it's 20-something maybe lines of XML. So, I showed the previous slide, had the recovery behaviors on it. So this kind of shows you the more now filled in picture that I showed you before with the recovery behaviors on the right here now, because that's your fallback flow if you fail the main flow. And so there's a recovery server over here with a spin action plugin, and you also have your services for your clear global and local cost maps. So in ROS2, they introduced a concept called lifecycle nodes. If you're familiar with those, you know what they do, but they basically allow you to, it's a built-in state machine within the base class of the node. So you can, when the node first, when you first construct the node, it comes up into the unconfigured state. And then you can use a service interface to change the state of the node and basically walk it through the state machine to get it to an activated state. So we took advantage of this in Navigation 2. We moved all the nodes to lifecycle nodes. And this allows us to have a very nice, well-defined bring-up, startup flow so that our nodes can come up in order of what they are dependent on. And, you know, truth be told, when we first ported everything to ROS2, with all the discovery traffic that was happening on in DDS, there was times where it was very difficult to get everything up and working. And once we moved to lifecycle nodes and we were able to do a more controlled bring-up flow, it became much more stable and reliable. So. If you want to know more about lifecycle nodes, this is taken directly from the ROS2 design documentation. You can go look that up. In order to control this, we created a lifecycle manager node. And so with that, we can feed it a list of nodes that we want it to control. And it has its own actions interface, or I mean, service interface there, manage lifecycle nodes where you can basically tell it like start up the whole system, shut down the whole system, pause the whole system, resume, et cetera. And then it will do that for all the nodes in the node list. And if you want it to just automatically bring everything up, which is the default behavior right now, then you just set a parameter in the launch file called auto start to true, and it will automatically walk them through in sequence. You define the sequence through the node list. A new thing we've added since dashing that's here now in Eloquent is the plugin interface called Nav2 Core. And so there's now plugin interfaces available for the global and local planners, recovery behaviors, goal checkers, and exceptions. Another new package we added for ROS2 is the Navigation 2 Bring Up package. So this package, you know, just like it sounds, it's basically some launch files and some examples, and makes it easy for you to just bring up the navigation stack with some good default configurations, et cetera. And it's, of course, there's parameter files and stuff in there that let you also configure it for your robot. It's kind of a reference reference launch system, I guess you would say. So one of the other things that came from the request for input from the community was there was, it was pointed out to us that in ROSCon, a lot of the testing was done basically manually on the physical robots. So like one of the maintainers told us that at one point he was testing every pull request on actual hardware before he would merge it. And we didn't see that as a sustainable practice in the long run. So we wanted to add CI that would automatically test every pull request for us, which we have. And so we created a top-level system test for doing that. And so it launches Gazebo in a headless mode, so it can run within a Docker container. And it launches a robot, obviously inside of Gazebo, and sends it commands to navigate, and then verifies that it actually reaches the goal. And it's a very simple test in concept, but it actually has found a lot of issues over time, and it's allowed us to have, it takes like less than a minute to run the test, and it basically gives us a full end-to-end test of the whole stack, at least at a smoke test type level. So this is a picture of the system with the system test in place. So you can see the test system node is driving the navigate to pose input and checking the outputs. And then you have Gazebo is acting as your sensors and your base controller. So as I mentioned, this has been very useful for us. It's allowed us to find a lot of issues, not just with navigation, but with the underlying ROS2 implementations. We can run the test hundreds or 1,000 times overnight, and so it's allowed us to find the things that only happen, one time in 100 kind of level of issues. And so with that data, we've worked with AD-Link and with eProsima, and basically they were able to reproduce some of these failures that we only see like one time in 100, and they were able to therefore fix underlying issues in the down low and the DDS layers. So and as you can see, we drove the pass rate by doing this. Like previously, our test was passing about 85% of the time on dashing, and then we were able to drive it up into the high 90s for eloquent. And there's still some, onesie, twosie type things that are still happening that we're still working to debug, but this gives us a good tool for doing that. So to summarize, Navigation 2 is, a key to overall ROS2 functionality and adoption. We have done some re-architecting of navigation in Navigation 2. We've added behavior trees, lifecycle nodes. We've tried to make it more customizable and reliable. We've added bring up launch files, and we've added system tests for CI. Our dashing release is available, for binary install, and our eloquent release we're working on right now, we'll have that out by the end of the year. So. Future plans in the short term, we're porting another local planner to use the plugin interface. The timed elastic band planner, which a lot of people have asked for. We're working on improving the system performance. We're obviously working on improving test coverage. We have actually a lightning talk on later today that will be given by Mali here on a random map generator tool that we've got that we're going to be using for testing robots in all types of random places. And then Obviously, we're trying to increase community involvement as well, and get, we welcome more people to come join and help us with this. So right now, as we're wrapping up Eloquent, we're starting to look forward to what we're going to do for the F-Turtle release, which is going to come out in mid-2020. We have kind of a backlog list of things that we could do and that we would prioritize, but we are also inviting the community to tell us what they want. So you can go to our repo and take a look at what issues are there and upvote the ones you like. We're also working with academia. We're based in Oregon, most of us are, so we've been working with the local universities there, trying to get them ramped up on how this works. I want to make sure to give credit to the entire team here. I'm here in representative of them, but this has been a team effort. You can find everybody on GitHub with these GitHub handles here, so. Also, I'd like to thank some of our partners that maybe haven't been direct contributors to the project. Well, some of them have, but in different ways, different levels. So Robotis, they've been very supportive with the TurtleBot 3. We're using that for most of our simulation testing, and they've been very responsive to any issues we find. Rover Robotics, who hopefully you guys saw Nick up here earlier, talking about the work they've been doing. They were early adopters of Navigation 2 on their robots. And Dan Rose, who's not here, I want to make sure, point out he was a big contributor as well. Yunji Robotics, they've been early adopters as well, and they're our demo partners. If you haven't been to our booth yet, you should go there and see their robot that's also running Navigation 2. OSRF, of course, has been very supportive. Everything that we've had problems with, and like any of the other layers of the stack, they're very responsive on. And thanks to Ruffin as well for setting up and maintaining our Circle CI. So lastly, I'll just say, please come try Navigation 2. You can either install it from the Debians, or if you want to kind of get the Eloquent preview, you can go to our repo and build the master branch now. Please feel free to start contributing, submit issues, PRs, etc. I should also mention we run the Navigation 2 working group, which is a weekly thing, and anyone's welcome to call in and join. We're in the process of moving this to Google Groups, so if you want to join, you just need to go add yourself to this Navigation Working Group invites list, and I'm in the process of working with Tully to get our current calendar invite moved over. Once I have that, then you'll get the invites. So, and then if you want to direct message me, you can direct message me through Discourse as well. So thank you very much, and I'm open to questions.
Okay, so we have time for about 2 questions. So if you have some questions, please go to the microphone to ask your question.
Thank you very much for the presentation. From the presentation, I think it's basically depend on cost mapping. So how do you think supporting outdoor autonomous driving applications like delivery robots and autonomous vehicles, like HD road network maps?
Yeah, so, I mean, the whole thing is designed to be extensible. All the planners are replaceable, all the sensors can be, swapped out, and the behavior tree itself allows you to customize the logic flow. So, in theory, that's quite possible. It's just a matter of writing the right action servers or the right planners for your application.
Okay, thank you.
Could you comment on the performance, reliability, and of the current software stack? In terms of performance, in terms of maybe the area, the sort of areas that it can navigate in and so forth and map.
Oh, you mean like Melanie was saying, like, you know, million square foot warehouses kind of thing? Well, I mean, I think, yeah, you're going to be limited more by like your data in those cases, right? I mean, the algorithms themselves are not limited in that regard.
And reliability and, you know, code quality as it currently sits in the
yeah,
in the repo.
we've been, you know, definitely focusing on code quality and reliability. As I mentioned, like with the system test, you know, we're definitely trying to weed out the things that happen, you know, 1% of the time or less, right? And yeah, we're going to continue to do that. We're going to expand our test suite, in fact, and test more and more different, you know, scenarios. So,
Great, thanks.
yeah.
All right, I'll let one more question.
Can you give us an insight on the issues you had, like 1 out of 100 times, and you could caught only 1 out of 100? I'd be pretty curious.
I couldn't hear the last part of what you just said. Can you repeat?
So the issues you caught, you said in simulation, 1 out of 100. An example?
I mean, yeah, most of those were, you know, they were race conditions that were either happening in RCL CPP or RMW or the underlying DDS implementations themselves. One of the first things we would try is if we hit one of these is we would run, like say we were running with fast RTPS, we'd switch out to like Cyclone DDS or one of the other DDS implementations to see if we see the same behavior. And if we did, then we, you know, kind of figured, oh, it's in one of these other, you know, the ROS2 layers, not the DDS layers. But yeah, we found some latent bugs that were in there that were really hard to find unless you had a lot of nodes running and trying to do things like discovery at the same time.
Thanks.
Yeah.
All right, well, thank you very much, Matt.